Hello everyone, welcome to the Introduction to Mechanical and Industrial Engineering course, MEC 130. This is a new topic which is thermal and energy systems. As we agreed over this course, we're just giving you an overview about the different topics that are of interest to both mechanical and industrial engineers. Or in other words, what are the different courses or subjects that you are going to study for your major, whatever it is, mechanical engineering or industrial engineering. One of them, which is common between both mechanical and industrial engineering or engineering in general, is thermal and energy systems. So as we discussed over the previous lectures, we define the force as a kind of interaction that would be generated between different objects, or even as a kind of interaction that can be used for merely changing the state of an object. We define the state of an object that it could be defined by a specific location of the object and the specific speed of the object by which is moving. So this is a state. Any object, it has a certain state, and somehow this object, it overcomes any changes to its state. So it means that it is not that easy that we can simply change the state of an object without doing anything. That we have at least to apply a force over the object, and this force, it should be big enough to change the state of this object, as we define the force in the previous topics or the previous chapters. Work is the endurance, something which is related to the force, definitely work. It means to exert a force. This indicates that you should do some work. And the work in terms of physics, it could be considered as the endurance of the force over a distance. Like simply as we knew from physics, or even as you studying in the physics class, that the work, it is the force times distance. So like this piston, for example, in order to push it, so this piston, it is located at this position. So in order to push it at certain distance, delta D, so delta D, this stands for the distance for which you are going to keep on applying the force, pushing this piston forward. So if you multiply the force times the distance, this is going to give you the work. So the work, it could be considered as the endurance of the force over a distance. And this what distinguish, so the work is kind of energy. We could consider the work as energy. And this, for example, probably you may have a guy who is strong enough that he can do the work, the force, he can provide very huge force, but unfortunately he won't gonna able to apply this force for a long period of time or a long or a large distance. Like for example, pushing. For example, if you have a box that is already sitting on the ground, you may have the capability to push the box by a force. So it means that you are strong enough to push the box, but it is not necessary that you're gonna push it for a long distance. For how far do you be capable of pushing this box? I mean the distance. So for how far is a distance that you will be able to push this box? So as the distance increases, it means that you have the ability to exert more work, you have the ability to exert more energy, it means that you are more energetic. So the energy, it is not related to the force itself as much as it is related to the endurance of the force over a distance. So that's why we could count the work as a form of the energy. So the work, it could be defined as the endurance of the force over a distance, and it could be defined as the force times the distance. And definitely that we knew that the force, it is measured in terms of Newton, and the distance, it could be measured in terms of meter if we are working with the international unit system. So this is gonna give us the work as Newton times meter. If we are working with the inch system or the American system, this should be in pound. And in that case, the distance, it could be in terms of inch. So this is going to give us as a pound inch, which indicate the unit for the work, which is going to be the pound inch in that case. And something that also you should understand, that the Newton meter, it is equivalent to joule. And we knew from physics that the joule, it is a measure of, or the unit of the energy. So that's why we can say that the work, it is a form of the energy, but energy that we give. So energy, it is the measure of the ability of an object or a mechanical system or someone as a human being to do something. So the capability to do any work, this requires energy. So the measure of this ability is the energy itself. The object or the mechanical system or the system can convert any work delivered to it into another form of useful energy. And that's why we're going to say that or that the energy is generally conservative, or conservative. It means that it is maintained, or in other words, as much of energy you give as you will receive. So if you're going to give a certain amount of energy, you're going to receive the same amount of energy. Why? Based on the conservative energy principle, or based on the fact that the energy is conserved. But it's conserved, but it can convert from one form to another form. Like, for example, you could give a work, and then this work, because it is energy, this is like energy that you give, which is the work, and for some reason is going to convert into another form of energy, like heating energy, like heat, or it could be converted into kinetic energy that is gonna need it to push an object to move. So anyway, it will be converted into other form, but it will be conservative, it will be preserved, it will be used. So if you give the amount of energy, you're gonna take the same amount of energy. Make sense? So now we define the force, we define the work, and we said the worker is a form of energy. We define the energy. How about the power? The power is a concept that is slightly different than the energy. The power, it could be defined as the energy per unit time, which is energy per unit time. So for example, if the energy it is measured in joules, and the time definite is going to be measured in second, this is going to give us the power as joule over second, which is equivalent to watts. So the watt, this is the equivalent to the joules per second, which is the energy per unit time. We could also understand the power as the endurance of the energy over a period of time, or the capability of the system to give the same amount of energy for a certain period of time. So this is going to give us the power. So how much of energy that can be delivered in a unit of time, and somehow we could use it to measure the ability of the system to give energy for a period of time. This could be also related somehow to the power. So the power, it is a measure of the energy in relation to the time, but the energy, it is the measure of the force in relation to the distance. So the energy, it relates the force that you are applying on an object to the distance that this object is going to move. If we're going to talk about this kinetic energy, for example, as a form of the energy, but the power, it relates the energy to the time in such a way that the energy, the power, it is the energy per unit time. So now what we are going to do, we are going to discuss the different forms of energy. We are, as engineers, whatever mechanical or industrial or any other major of engineering, definitely we should deal with some energies, because we're going to exert some work. This is going to be a form of energy. Also, we are going to receive a work, an energy. And as we said that the energy is conserved, it means that, but it can be converted from one form to another form. So what are the different forms or different types of energy that we would experience as engineer? This is what we are going to discuss. The first one of them, which is the gravitational potential energy, it is commonly known as the potential energy. So the gravitational, because the potential energy, it is not necessary to be generated from a gravitational force, but it could be generated from elastic energy. Like this is like the elastic energy. It is also a form of a potential energy. In general, what does it mean, a potential energy? Whatever it is, gravitational potential energy or elastic potential energy. The potential energy, it gives the object the capability to move without any external need or without any external force. For example, something that we could understand about the energy and the work. Like, for example, if we do have this box and you're going to apply a force over this box, so this box is going to move as a result of the force. So in that case, you are applying an energy. You are giving energy to the system so it would move. You are giving energy to the system to do something. So the energy that you exert on this box, on this object, is gonna make it, or the box or the object is gonna take this energy, is gonna use this energy to move or to do any other thing, whatever it is. But in case that the object would have the capability to move without any external force, or to move without any energy that it should be given to it, it means that this object had the potential to work alone, had the potential to move alone, has the potential to do something without any external energy, this is known as the potential energy. So the gravitational potential energy, it is one form of the potential energy. To understand it well, so let us define first what does it mean gravitational potential energy. If an object is elevated above the surface of the earth with a certain height or a distance from the earth or the ground as h, it has the potential, we're going to say that this object has the potential energy to move vertically towards the surface of the earth or the surface of the ground. So for example, if let us assume that there is a table, and for some reason that you already, this table definitely it will be elevated from the ground. Elevated from the ground, it means that the surface of the table, let us consider this ground as a datum. This is our reference. And there should be like a height distance as h, which refers to the distance from the top surface of the table to the ground. And for some reason that you're already setting an object over this table. So we're going to say that this object now, the object is stationary at a certain state, which is stationary, not moving, had zero velocity, nothing wrong or a change that is going to change over the state of this object unless you do something, right? But for example, for some reason, if we decided, so first of all, this object now it is not moving. It has no energy. There is no external energy that we are applying on this object to move. But it has potential to move. What does it mean, potential? This potential energy will show up once we try to remove quickly the table underneath the object. For example, if you decided for some reason to remove the table very quick and leave this object as it is, so just pull this table quickly, so this object will start to fall down on the ground. Why? We didn't apply any force. Why this object is going to move down? Because of what? Because of the gravitational force. This gravitational force gives potential, and this potential, it is stored inside this object somehow. It is stored or preserved for this object as long as the table is already there. But once we remove the table quickly, the object will start to move by itself. There is no any other external force that you're going to apply on the object to move. So while this object is going to move, why it's going to fall down on the ground and moving this vertical distance h till it will hit to the ground, this indicates that there should be some energy there. But this energy, it is not external. We are not the one who are applying this energy, but instead this energy, it is potential, stored somehow or preserved to this object because of its elevation from the ground, because it is at a vertical distance, a vertical height from the ground. Once we remove the table, it's gonna recall this potential energy. It's gonna take this restored energy and to move down to the ground. This is known as the potential energy. So once we set an object on the top of any other surface that is elevated from the ground, we're gonna say that this object has the potential to move, has the capability to move, but we are preventing the movement of this object because of the table. But once we remove the table, it's gonna fall down. It's going to recall this potential, it's going to take this stored potential energy within this object that is given to this object to move down without any need to push it down with any external force or an external energy. So this is a type of energy known as the potential energy that comes from the gravitational force that acts between the earth and any object that is located within the circumference or the environment of the earth. So we're going to say that this object has the potential to move, has potential energy to move vertically toward the surface of the earth or the surface of the ground. And this potential energy, definitely, it depends on the weight of this object or the mass of the object. That we can define this gravitational force as plus or minus, and we're going to talk about the sign, whatever, when it should be positive, when it should be negative, time the mass, time the g, which is the gravitational acceleration, time h. So M stands for the mass of the object that is elevated at a certain height from the ground. And the mass, as we knew from the discussion for the unit systems, according to the SI, the International Unit System, it should be in kilograms, or it could be in slag according to the inch unit system or the American unit system. Make sense? So if you multiply the mass times g, which is the gravitational acceleration, and you should understand that the gravitational acceleration, it is 9.81 meter per second square. This is a constant value for the gravitational acceleration at any point, at any location over the earth. This is the gravitational acceleration as being measured by the physics, and it is 9.81 meter per second square. As long as we are working with the metric system or the international unit system, if we are working with the inch or the American unit system, is going to be equivalent to 32.2. So the 32.2 feet per second square, it is equivalent to the 9.81 meter per second square. Depending on the unit system that is given to you in the problem, when we are calculating this potential energy, we're gonna plug G either 9.81 or 32.2 depending on the unit system. H, this is the height from the distance or the vertical distance from the datum. We said that you should set up a datum. Datum, this is like a reference. Like for example, if I decided to measure the potential energy of this object with respect to this reference. So let us consider this datum here. So as you can see, at this instant, I'm going to say that this object has the potential to move down. All the time, the gravitational potential energy, it should be directed downward. That required to move the object down. So this object is going to move down to fall into the ground or to move towards this datum as long as it is elevated above the datum. So that's why in that case the potential energy is going to be positive. So again, when the potential energy is going to be positive in case that the object that it already has a potential, as we said, if you set any object over the table, we're going to say that this object had the potential to move down towards the ground. So it is in general, to make it more general, it is not necessary to be applied on the ground or a specific ground. We're going to refer to a datum. So this datum or this datum, it is a reference. So as you can see, the object now, it is above the datum. So that's why it has a positive potential energy. Its gravitational potential energy is positive. Why? Because it will move the object towards the datum. The object is going to move down towards the datum. So in that case, it's going to be positive. But for example, for some reason, if we decided to refer to another datum, refer to another surface that is above the object, or in other words, that the object, it is below the datum. So in that case, if we're going to consider the datum in that case, and in this case, this distance even, it could be h, the same height even. So with respect to this reference, with respect to this datum, the object has a negative potential energy. Why? It is located below the datum. Why? Because if you remove the table, the object will not be moving towards the datum, this blue datum, but instead it's going to move in the opposite side. So that's why it should take in a negative energy. So general, when it should be positive in case that the datum above the, the object above the datum or the reference that you choose, so it will have a potential energy. This potential energy should be positive. But in case that the object is below the datum or the reference that you choose, so in that case, the potential, we're going to say that this object has potential to move, but in the opposite direction, in the negative direction. It won't going to move toward the datum, but it will going to move far from the datum, indicating that we're going to have a negative potential energy. This is how we can decide for the sign. The choice of the reference, it is totally up to you. We can, depending on the problem that we solve, we should set a datum. We should define a reference that we're going to refer to it, all the different forms of the energy. And again, this is the gravitational potential energy. It is one of the forms of the energy that we are going to discuss. Make sense? Another form of the energy is the elastic energy. Also, it could be named as elastic potential energy. So it is also another form of the potential energy. So this is one form, the gravitational potential energy, that comes from the gravitational effect over any object that belongs to the earth. We do have also the elastic energy, and it is a form of the potential energy. Why? What does it mean, potential? As I mentioned, this is the kind of energy that is preserved to an object, that is gonna make the object move by itself without any external help, without any external push or force or energy. It's gonna make the object move by itself, like the gravitational acceleration in that case, or the gravitational force. In addition to the gravitational force, the elastic energy or the elastic force, it gives potential to objects to move by themselves. To understand it more, let us assume that you're handling this box and there is a spring. At this instant of time, the box is not touching the spring, so the spring is free. There is no tension or stretch in the spring, there is no compression in the spring, nothing in the spring. So the spring is free. There is no forces acting on the spring. Then for some reason you decided to keep on pushing the box against the spring, and even you're gonna push it hard till you're gonna compress the spring. So the spring is compressed in that case with a certain distance as x. And then you push the box this certain distance x, then you stop. And you're gonna keep on holding the box by your hand. So at this instant of time, the spring is compressed and pushes against the box, but because you are using your hands, you're just holding the box in place. So what is the current state of this box? It is stationary, not moving, under static condition, has no velocity. So this is the current state of the box. But for some reason, if you remove or release your hand, release the box, just remove your hand, what's gonna happen? You're gonna find that this box will be pushed hard and it's gonna slide in this direction as already shown in this figure. It's gonna move to the right. What makes the box moves? As we say, to achieve a motion, this requires energy. It means that the box, since it had been moved, it means that it has been given an energy to move. And this energy definitely is gonna be coming from the spring. The spring is the thing that is gonna push the box to move in the right direction. But what is the type of this energy? This is a potential energy. The same concept like this case. We're gonna say that this box had the potential to move down, but we would like, or we would need to remove the table to allow this box to move down. So it had the potential to move, and it's gonna take this energy, this potential energy, when it is needed. The box is gonna take this energy and use it to move down when it is needed. The same thing here. As long as you are holding the box by your hand, at this instant of time, this box has potential. It has a potential energy that is stored within this system. And once you remove your hand, the object is gonna recall this stored energy to use it to move back or to move to the right direction. This energy is going to be stored inside the spring. And this is the same concept as the elasticity, as we discussed before. When we were discussing the tensile test, we said that within the elastic region, the material had the capability to restore its original dimensions one more time once we remove the applied force. Once we remove our hand, this spring can restore its original dimension again, which will be straightened back with no tension, with no compression that is going to generate with the spring. So once you remove your hand, the spring, it will try to restore its original position, its original length, and in that case, it's gonna provide some energy that is gonna push the box. This energy is known as elastic energy. So that's why we are giving the name elastic, because it works the same concept as the elasticity when it is compared to the plasticity when we were discussing the stress strain curve or the tensile test of the material. We said that within the elastic region, the material can restore back again its original dimensions, and this requires energy. It means that if you give energy, apply a force over the material, the spring is gonna take this energy Because to push the box, while we are pushing from this instant to this instant, we have applied some force. We have applied some work, and we said that this work is energy that is going to be stored. The spring is going to absorb this energy and is going to store this energy. And now, as long as you are holding the box in position by your hand, the energy it is already stored and saved inside the spring. Once we release our hands, the spring is gonna recall and is gonna use this stored energy, which is an elastic energy, to push the box on the other side and stretch back again. So this is another form of the potential energy. Is gonna make the object move by itself without any external excitation or without any external force acting on it, but it comes through an elastic element which is known as a spring. So this is the spring. So the elastic energy, which we can refer to it as UE, but the UG, G stands for the gravitational acceleration, but UE stands for elastic energy. It is a stored energy in an elastic material or a spring, like a spring. This energy is used to return the material or the spring to its original size one more time, and that's why it will be stored, then it will be recalled to give potential to this object to move by itself without any external force. Make sense? This elastic energy can be represented for a linear spring into this form as 1/2 K. This is a constant of the spring, is known as the spring stiffness or the spring constant. The spring, it is one of the mechanical components, and any spring, it has a specific value known as the spring constant. It is measured by Newton per unit length, or force per unit length, which is Newton over meter, or pound over foot, in case that we are working with the inch system. S stands for the amount of stretch or compression. As we explained here, we explained how the energy is stored in the spring under compression. The same thing is applying in case that is still applied in case that the spring is stretched. So no matter what, the spring is under compression or under stretch, compression or tension, the amount of stretch or even amount of compression, which it should be measured as a distance. So this like x here. So this x, this is the s into this expression, into this equation. If you square the distance, the compression or the stretch in the spring, times the spring constant, times 1/2, this is going to give you the potential energy due to the elasticity that is going to be stored within this spring, and this potential energy that is going to be the spring that is going to use to restore back again to the original dimension as shown here in the animation. Make sense? So since if you multiply it Newton over meter times meter squared, this is going to give you Newton meter, which is joules, and this is energy. So that's why the joule, it is a measure of the energy. Pound foot also, this is the measure of the energy in the American unit system. Make sense? So this is another form of the potential energy. The third form, another form of the potential energy and another form of the energy in general. But remember that the potential energy are two types, either elastic potential energy or gravitational potential energy. Another form of the potential energy is the kinetic energy. Like if you're gonna apply a force or a work over an object, this work could be converted into a kinetic energy. The kinetic energy depends on the motion. It's gonna give motion to the object. So any object that is stationary has zero velocity, that is not moving, definitely it has zero potential energy. So the potential energy is only given or described for objects who are moving, that are moving. Any object that moves, it has a it has a kinetic energy to move. Or we at least should apply a force on it or a work on it, and this work, it will be converted into kinetic energy. So it is the energy that generates due to the object's motion. This kinetic energy equals the 1/2 times mass v square, as long as the object moves or exhibiting type of motion known as the translational motion, like it translates along a certain direction as a linear motion. Like for example, if you do have a box, in that case, that is sitting on the ground, and assume that this is position 1. At this instant of time, at this position, this box would have a certain velocity. Then if Assume that it was stationary, not moving. So what should be the speed or the velocity of this object? It will be 0. So V stands for the object's speed or the object's velocity, which it should be measured as meter per second as long as we are working with the metric system, or foot or feet per second as long as we are working with the American system. Make sense? So assume that the object now it is stationary, not moving at position 1, and for some reason we're going to apply a force on it. So this force is going to keep on pushing this object for a certain distance. If you multiply the force times the distance, assume that this is the distance and this is the new position that it will be for the box. So this is position 2 for the box after the pushing with the force F. And initially the velocity should be 0. When we apply the force, the box will start to speed up. It means that the speed of the box is going to keep on increasing somehow till it will be at this instant of time will be with a certain value. So V1 here was 0, V2 here will be with a specific value. At this instant of time, the box will have a kinetic energy, will have an energy that comes because of the motion, this energy known as the kinetic energy that depends on the speed of this object. If we can allow this box or this object to move more, so its speed is going to increase, or probably for some reason because of some reference roughness over the surface, the speed could be decreasing. Anyway, the speed of the object is going to change, and this is going to give another different energy or kinetic energy to this object. But anyway, there is a kinetic energy that is going to be given because of the work. That is what is going to be generated because of the work that we are applying over this box. We are pushing with a force for a certain distance as S, for example. So if you multiply the force times S, this is going to give you the work that you are applying or exerting over the box. This work will be converted into kinetic energy, and this what gives the object the potential or the energy to move with a certain velocity. This kinetic energy is known as 1/2 the mass of the object, because the kinetic energy depends on the mass of the object. For example, if you're going to apply a certain amount of work, so the work is constant that you're going to give to the object, but you are going to apply this work over an object with a small mass, over an object with a small mass. So this speed of this object will speed up faster. It means that the speed of the object will be bigger. Why this? Because you're still applying the same amount of force, of work, over the object, but the object with a lower mass, smaller mass. So it's going to speed up more. The speed of the object is going to increase. If you are going to apply the same amount of force, the same amount of work over another object but is heavier, this object has a bigger mass, so it will not be speeding up the same way as the light mass or the small mass object. The small mass object will be moving faster than the other one. The one with a bigger mass is going to move slowly in comparison to the object with a lower mass. Make sense? So it means that the mass and the velocity, they do have some relation to each other. So this V, this is the mass M, stands for the mass of the object, which should be measured in kilogram or the slag, depending on the unit system. So if you did the multiplication, you're going to end up in terms of joules. In case that we are working with the SI unit system or the US unit system, you're going to have pound foot or as the unit for the kinetic energy. Make sense? Another form, or yeah, so these are like these three types of forces, of energies, these three types of energies, commonly known as mechanical energies, that comes from a mechanical element like the spring or the elastic energy, gravitational force, or even the kinetic energy. They are commonly, we can give these three types or forms of the energies as a mechanical energy. There is a condition that would relate the kinetic energy to the elastic energy, to the potential energy or the gravitational energy, which depends on the concept of the conservative energy or the conservation of energy. As we mentioned that the energy, it is conserved, but it can be converted from one form to another form. Like probably you can have a kinetic energy that is going to be potential energy converted to a kinetic energy. A wall that is going to convert it into a potential energy, elastic energy, or converted into kinetic energy. It means that the energy can be converted from one form to the other form, but it should be preserved or conservative. Conservative, it means that there is no loss in the kinetic and the energy as long as the system is conservative. There are some conditions for a conservative system. But anyway, even if it is non-conservative, it will be converted into another useful form that we can use it. But anyway, the energy is still there. So, how we can relate the kinetic energy, the elastic energy, or the potential gravitational energy for an object? Because for example, you probably in general, let's say like assume that you have an object like this box, and this object is connected or linked to a spring that is pivoted at this point, and assume that this box is over like this ramp. This is like over this surface here. So if we define the datum at this reference, like a reference here, if we assume that this is our datum point or line, this is our reference, so we're gonna say that this object has potential to move down, right? If we just give a little bit push, or even if we remove the ramp underneath this box, the box is gonna fall down on the ground. So first of all, it has a potential to move down that comes from the gravitational acceleration. Why? Because it has a vertical height from a reference, from our reference, our datum in that case. So we're gonna have, it has a gravitational potential energy at this position. Also, it is connected to a spring. So the spring is going to give another form of energy at the elastic energy, U elastic. And once any push that, think of it like, if, for example, if we push this box to slide over the ramp, so it's going to move down, moving the box, it means that there should be some kinetic energy. It has a kinetic energy. So the question is, this object in this problem, in this engineering application, it will have different forms and different types of energies. How we can relate these different types of energies together? We have to apply a concept or a relation or a theory. This concept is known as the conservative energy or the conservation of energy principle. This is known as conservation of energy principle that is applicable to any engineering system, whatever it is. So the energy is required to move, that is required. The energy required to move an object between two different positions is conserved. This energy that is required. For example, for some reason, if we would like to move it from this point up to this point. So this is going to be the location 2, location 1 and location 2, or position 1, position 2. So we are interested in moving this object between these two different positions. So we have to give it energy. This energy will be conserved and it will be converted into another form at the second position. But you should understand that the sum of the energies, all the energies at position 1, of the object at position 1, it should be the same sum of the energies at position 2. So again, the sum of the energies, because as I said, at this position 1, this object has multiple energies. 3 energies. It has a kinetic energy, it has a gravitational energy, it has an elastic energy. So the sum of these 3 energies at position 1, it should be equal to the sum of the 3 energies at position 2. So at position 2, there should be like UG, U elastic, U kinetic. Still the 3 kinetic energies will be there at position 2. But it is not necessary that so let us give it like some subscripts here to distinguish between position 1 from position 2. So assume that this is UK1. This is the kinetic energy of the object at position 1, when it is at position 1. UG1, this is the potential gravitational energy of the object when it is at position 1. UE1, this is the elastic energy of the object when it is at position 1. The same thing, these are the 3 energies when it is at position 2. Something that you should understand, it is not necessary that the elastic energy at position 1 equal the elastic energy at position 2. It is not necessary. In many of the cases, they're going to be different. Also, the kinetic energy of the object at position 1, mostly it's going to be different. It could be equal. But on many of the cases, in the usual scenario, in the usual case, the kinetic energy of the object at position 1, it will be different than its kinetic energy at position 2. The same thing is applicable for the gravitational potential energy at position 1. In many of the cases, it will not be equal to the gravitational potential energy at position 2. They may be equal or they may be different. In many of the cases, as I mentioned, they're going to be different. But there is a relation. What it is that the sum of the three energies, it should equal to the sum of the other three energies. So every specific energy, it is not necessary to be conserved. It is not necessary to be the same. It could be changing as a value, but it will be changing from one form to another form, making the sum of the three energies is the same at the two positions. Make sense? So UE1, it is not necessary to be UE2. It means that the elastic energy by itself, it is not necessary to be conservative. The kinetic energy by itself, it is not necessary to be conservative. The gravitational potential energy by itself, it is not necessary to be conservative. Conservative, it means that the energy should be the same, but it is not necessary to be the same. But the sum of the three energies is the conservative energy. The sum of the three should be the same, according to the conservative of energy principle that states that the sum of the gravitational acceleration, the gravitational energy, the elastic energy, the kinetic energy in position 1, it should equal to the sum of the gravitational, elastic, and kinetic energies at position 2. This is according to the conservative of energy principle. So again, the energy itself, one specific energy form, it is not necessary to be conservative, but the sum of the energies that acting over the object or that the object has at any position, it will be conservative at any other position. It will be the same. Make sense? So let us consider this example to apply the conservative of energy principle that we just discussed over this problem. So in this example, this is like a typical example. Assume that this is like a column that is standing fixed to the ground from this base and from the top. This, which is orange column, this is just like vertical standing column. And there is a collar. This collar, this slide, this collar is something that is going to slide over the column. It's going to move up and down. It depends. And this is a spring that is already fixed here or sitting over the ground, and it is somehow surrounding the column itself, and it has 400 Newton per meter. So the Newton per meter, this is K. You have to keep eye over the unit. I won't gonna ask you to do so many unit conversions, but the key condition that you should understand the different constants and parameters of these systems based on the unit. So we define that the spring constant or the stiffness as Newton per meter or force per meter or force per length. As long as we are working with the metric system, is going to be Newton per meter, or American system as pound per foot. So if you just observe the unit, you could understand what does it mean, this unit, or what this 400 refers to. This 400 refers to the K, to the spring constant. Make sense? And you'd have this collar or this object, which is going to, this slider that is going to slide over this vertical column. So a block or an object at A, which is located at point A, think of it like you just holding this slide or this block by your bare hands at this position A. So we're gonna say that this is position 1. It is important when you study or apply the conservation of energy principle to identify where is position 1, where is position 2, according to the given problem. So here, initially, the problem comes in this way, that we start by describing position 1, then we are going to ask you to do some calculations at another position. The other position is going to be directly position 2. So again, it works in this way. Like the problem starts by describing what's going on at position 1. Then you will be required to calculate. Once it is mentioned calculate or find or determine or do anything, the requirement, in the thing that will be required from you, it will be related to the second position, which is position 2. So the first step in the problem that you should identify where is position 1, where is position 2. So here he is talking about this block, this object that is located at point A. It means that at point A, this is position 1. It has a mass of 10 kilograms. This object has a mass. This block has a mass, so the mass of the object it is given by 10 kilograms. If it is released from rest, what does it mean released from rest? It means that initially we're just holding this box by hand. This block by hand at this position 1. Then I'm going to release it. I'm going to release it. So what's going to happen is going to fall down. It's going to move down. Why? Because of the gravitational force. Because it has a potential at this level to move down. Definitely it's going to fall down. Moving vertical till it will be applied or touching the spring and it's going to keep on compressing the spring. Make sense? But initially it was at rest. What does it mean at rest? At rest it means that it has no motion. It is not moving. It is stationary. And any object that is fixed or is stationary, it should have a zero velocity. So the first step in the problem is just to identify where is position 1. And at this position, there are some specific parameters that you have to identify. One parameter, which is the speed of the object or the velocity of the object at position 1, how much it is, and the amount of stretch or the compression in the spring, as long as there is a spring in the problem. Here we have a spring, right? So we should identify at position 1 how much of a stretch or how much of compression that we're gonna give it a name as S of the spring at position 1. How much is this stretch or compression in the spring at position 1? How much is the speed or the velocity of the object at position 1? So initially he said that this object has a mass of 10 kilograms, no problem. At position 1, it was at rest. So what does it mean it was at rest? It means that the velocity of the object at position 1, it was 0. Any object that is at rest, it means that it is stationary, not moving. It means has 0 velocity, has 0 speed. So the speed of the object it is 0 at position 1. In the meanwhile, how much is the stretch or the compression of the spring at position 1? It should be 0. Why 0? Because at position 1, the object it is not even touching the spring. The spring it is free. The spring is just sitting on the ground. There is no stretch. There is no compression in the spring. Why? Because the box is far away from the spring surface. So in that case, it means that the amount of the stretch or the compression in the spring is 0. So this S stands for the stretch or the compression of the spring at position 1. And V1, this is the speed or the velocity of the object of the block at position 1. You're gonna find the same two values but at position 2. In the meanwhile, but at position 2, for now just identify these two values. Make sense? Then he required to calculate. So what comes after the calculation, but after the word calculate or find or determine, this is a description of position 2. Now we identified where is position 1. What comes next is to identify the parameter and where is the position 2, where is the second position. Because to apply this equation, we have to know where is position 1, where is position 2. So what comes after calculate, this is a description about the position 2. So it is required to calculate the maximum compression in the spring. This is what is required. So what is position 2 then? Position 2, it is at the instant that this spring will be maximally compressed. At the maximal compression of the maximum compression of the spring. So how it works, this system? Initially we are holding the block by bare hands. Then we're gonna release it. We're just gonna leave this box. So it's gonna move down. It's gonna keep on moving down, move down, move down. Till what? Till it will touch the spring. At this instant, just touching the spring is not compressed, is not stretched, nothing wrong with the spring. But the box, it won't gonna just stand. The box is gonna keep on pushing and compressing the spring. It's gonna keep on compressing the spring till the spring will be compressed at maximum value. Then after that, the spring is gonna start to push, to rebound again the box above. Think of it like this box. It is a very huge box, and you just gotta release it from a very high distance over this spring. So it's gonna keep on pushing the spring down, compressing the spring down. Then the spring is gonna push against this box, and it's gonna rebound the box with a very high speed up. Forget about the rebouncing motion. Think of it, what is the maximum compression? So the box is gonna keep on moving till it will compress the spring. So after the compression of the spring, let's say the box will be here, and the spring will be squeezed over this small distance. So think of it like this is the new location of the box. So this is gonna give us the second position. So this is position 2. You are required to identify how much is the speed of the object at position 2, how much is the compression of the object at position 2. The same two values but at position 2. So as for the speed of the object, and this is tricky thing that you have to imagine what is going to happen to this object and this spring once we release it. So the box is gonna keep on pushing, the spring gonna keep on pushing and moving down, moving down, moving down. It means that there is a speed for the box. There is a speed of the block or the object as long as it pushes down the spring, till the spring will be maximally decompressed. The spring is going to reach to its maximum compression. It won't going to be able to be compressed more. At this instant, the box will not be able to push the spring further. The box will not be able to move down more. At this instant of time, the box will lead or will attain a rest. The box will be stationary at this instant. Why? It won't gonna be able to push more. So what does it mean this? It means that the speed of the box at the second position, which will be obtained at the maximum compression of the spring, it will be 0. Why? Because initially the speed of the box, it is very high. It is 0 at position 1. The speed of the box, it is 0. Then it's gonna start to speed up, speed up, speed up, speed up to be maximum once it touches the spring. Now the spring is not compressed. But once the box is gonna start to compress the spring is gonna slow down the object. So we started from 0 velocity at position 1, and the speed was increasing till the box or the block start to touch the spring. Then after that, the scenario will be different. We start from a very high speed at the instant of touching the spring, then the box will start to keep on compressing the spring. The spring is gonna work against the motion of the box. It's gonna work against the motion of the block, and it's gonna slow down the motion of the block. The block will start with a very high speed, and this speed is going to decrease steadily till it will be 0 at the maximum compression. And at the maximum compression, this is position 2 that we are talking about. So this means that at position 2, which will be obtained at the maximum compression of the spring, the speed of the object will be 0. But how much is the compression then? Initially the compression was 0 while the box is far from the spring, it is not touching the spring, but as long as the box is gonna keep on pushing down the spring, it's gonna keep on compressing, and the compression in the spring is gonna be increasing till it will be maximum. So S2, it will be the maximum compression that we are seeking. And the maximum compression, it is unknown. This is the requirement. This is what is required from us in this problem to solve. Make sense? So it is required here to find the maximum compression in the spring, which definitely is going to be equal to the S2. As I said, the first step is just to identify where is position 1 and position 2. And for position 1 and position 2, identify how much is the speed of the object or the velocity of the object at position 1 and position 2, the amount of compression or stretching the spring at position 1 and position 2, as long as there is a spring in the problem. If there is no spring, there is no need to consider S1 or S2. Make sense? Another thing is that you have to set up a datum. You have to identify a reference to calculate the gravitational potential energy. We said that the gravitational potential energy requires a datum. So let us assume, for example, that I'm going to choose the datum at position 1. This is the easiest way. To make it simple, assume the datum or the reference at position 1. And then you are going, with respect to this datum, you are going to calculate the potential energy at position 1 and position 2, referring to the same reference, to the same datum at the two positions. Make sense? So the first step is just to do this initial setup of the problem, identify this data. Then you're gonna directly start to calculate the different forms of the energies, the three forms of the energy: the gravitational potential energy, the elastic potential energy, and the kinetic energy at the two positions. So let us start with the gravitational potential energy, UG. The gravitational potential energy at position 1. Let us start at position 1. What is the expression of the gravitational potential energy? We said that it is plus or minus. It is positive in case that the object, it is above the datum. If it is below the datum, so it's going to be negative. And the mass GH, what is H? This is the vertical distance of the object from the datum. But how about if the object is already sitting over the datum, as in the case 1? At position 1, so if we're going to say this, it should be plus or minus mgh. So how much is h? H, it should be the height of the object, the vertical distance of the object to the datum. Now the object is exactly over the datum, is exactly at the reference. This indicates that this h equals 0 for the position 1. So anything that is multiplied times 0 gives 0. So this is going to give us the potential energy, the gravitational potential energy at position 1, it is 0. But how about the gravitational potential energy at position 2? You're going to still use the same datum, the same reference. So it should be plus or minus mgh, but at position 2. So this is like h1, it was 0. So equals. Is it positive or negative? The object at position 2, when this block moves down at position 2, it will below the datum. It will underneath the datum. So it will be negative since it is blue. And the mass of the object, it is 10 kilograms as already given, times the gravitational acceleration, which it should be 9.81. Why 9.81? One, because we are working with the metric system. Kilograms indicates metric system. Newton meter indicate metric system or international unit system. And we said that the gravitational acceleration, as long as you are working with the international unit system, it should be 9.81. Times h2. How much is h2? h2, it should be the height or the vertical distance of the object that is at position 2 from the datum. So how much is the distance from position 2, which it should be here, to the datum? How much is this height? This should give us h2, how much it is. As you can see, the distance 0.5 meter. This distance was given from the object to the top surface of the spring, to the instant that the box is gonna touch the spring. But the object is going to keep on descending, is going to keep on pushing down. It means that the h2, it is bigger than the 0.5. The difference between h2 and the 0.5 is this distance. This distance, it is S2, which is S maximum. This is the maximum compression in the spring. Why? Because, as I said, the box is going to keep on pushing the spring down. So it means that the distance, the total distance that the box is going to move down from position 1 to position 2, this is h2, is going to be the 0.5 plus the S maximum, which we have no clue how much it is. So it should be h2 equals 0.5 plus the S maximum, the maximum compression that we don't know. So this definitely, if we're gonna do some simplification to this some calculations here, we're gonna end up with 98, 10 times 9.81 times half. So this is gonna give us the negative of 49.05 negative the 98.1 S maximum. So this is the maximum compression. This is going to give us the potential energy at position 2. So potential energy we have done of the calculation of the potential energies at position 1 and position 2. As you can see, they are both different. Why? This indicates that the potential energy, it is not necessary to be conservative. But the all energies acting over this object at the two positions should be conservative. Make sense? Now let us move to the second type of energy, which is the elastic energy. How we can calculate the elastic energy, U elastic. The elastic energy we are required to calculate the elastic energy at position 1 and position 2. The elastic energy is a simple thing. We define the elastic energy as half K S square. K, this stands for the stiffness of the spring. S stands for the stretch or the compression in the spring. So simply we're going to say that this elastic energy is going to be half 1 over 2 the K times S1 squared. The stiffness of the spring, it will not change from position 1 to position 2. Why? It is a spring constant. It is constant to a specific spring, and we are not going to change the spring from position 1 and position 2. So it means that the K is still the same. The only thing that it changes between position 1 and position 2 is the S. So that's why I required you to calculate S1 and S2. So S1 we already calculated by 0. So this indicates that the elastic energy at position 1 it is 0. But the elastic energy at position 2 will equal to 1 over 2 K S2 square. S2 square, this is the S maximum, the maximum compression. So it will be 1 over 2 Ks maximum square. So this is going to give us the elastic energy at position 2. So we have done or finished the calculations of the elastic energies at position 1 and 2. So now we're going to move to the kinetic energy. So the third type of energy is the kinetic energy. The kinetic energy, which is UK, where K stands for kinetic. We define the kinetic energy whatever at position 1 or position 2. So the UK at position 1, it should equal to, according to our definition of the kinetic energy, it is half the mass of the object times its speed or velocity at position 1 or position 2. So definitely this object, it is a solid object, so its mass will be the same at position 1 or position 2. So there is no changes over the mass, which is already 10 kilograms. So this is going to give us half the mass, but the only thing that is going to change between position 1 and position 2 is the velocity or the speed of the object at position 1 will be different than, could be different, or it could be the same than position 2. So at position 1, what would the value for the speed or the velocity of the object at position 1? It would be 0. It was 0. This indicates that the kinetic energy will be 0. And then you're going to calculate the kinetic energy of the object at position 2, which it should be half the mass of the speed of the object at position 2. So the speed of the object at position 2, we got it also by 0. But as I said, it is not necessary to be 0. It could be with any other value, no matter what is, we can identify this value, or it could be given to us. But for this case, based on the investigation, based on the understanding of this problem, we found that the velocity of the object at position 2, it should be 0 as well, indicating that the kinetic energy of the object, it will be 0. So as you can see, the object started with a 0 kinetic energy, and it ended up with a 0 kinetic energy as well. But the question is, so what does it mean? First of all, what does it mean a 0 kinetic energy? A 0 kinetic energy, it means that the object has no motion. The object, it doesn't move. But as you can see here, the kinetic energy at position 1, it is 0. And then at position 2, it became also 0. So how come that we say that the object didn't move? No, the object is already moved. The object is already moved. But for example, the object at this instant, the object is moving down. If we take a picture of this object that while it descending or moving down, at this instant of time, it will have a specific kinetic energy. It will be with a value. There it will have a different kinetic energy. There it will have a different kinetic energy. And as you can see, as it moves freely over this column before touching the spring, its kinetic energy is going to keep on increasing till it touches the spring. Once it touched the spring, the kinetic energy and the box is gonna take use, or is gonna use this kinetic energy to push the spring, but the spring is gonna slow down the object, is gonna slow down this block, and in that case the kinetic energy of the object will start to keep on decreasing till it will be zero one more time. So since the kinetic energy, it is zero at position 1 and zero at position 2, this doesn't mean the object didn't move. No, the object was moving, and the kinetic energies between the two positions, it was changing, but suddenly for some reason that the kinetic energy, it was zero at position 1 and it was zero exactly at position 2. But between 1 and 2, there was a kinetic energy with a specific value. Make sense? This is something that you should understand. Once you calculate the gravitational potential energy, the elastic potential energy, and the kinetic energy, you are going to apply the conservative energy principle. We see that this principle states that the sum of the energy at position 1, it should equal to the sum of the energy at position 2. So we do have the gravitational potential energy at position 1 plus the elastic potential energy at position 1 plus the kinetic energy at position 1. It should equal to the gravitational potential energy at position 2 plus the elastic energy at position 2 plus the kinetic energy at position 2. Then your objective is just to plug the value that we got it or calculated for this different kinetic energy. So for the UG1 it was 0, but UG2 was with this value. So this should be 0. Plus the elastic energy at position 1, it was also 0, right? It was 0 here. And the kinetic energy at position 1 was 0. So 0 plus 0 equals. So all the left side is 0. The right side, the gravitational acceleration at position 2, it was equal to the negative 49.05 negative 98.1 times the S maximum. This is the maximum compression in the spring. Remember that he requires how much is this maximum compression in the spring. It is unknown. Plus this is the gravitational energy. The elastic energy, it was half K times S maximum square. K, it was given to us by 400. So half times 400, this gives 200. So this definitely, this is 400, I'm sorry. So half times 400 gives 200 times the S maximum square. Plus the kinetic energy at position 2, which is already 0. So as you can see, we're going to end up with an equation. This equation has only one unknown, which is S maximum. So simply, we're going to end up with this quadratic function of 200 S maximum. If we just arrange this equation, S maximum negative 98.1, S maximum negative the 49.05 equals 0. This is going to give us a quadratic function that you can simply use the quadratic formula, or you can use the calculator to calculate its maximum, how much it is. So if we decided to solve this expression or this quadratic formula, if you remember from the mathematics, that you can identify the A coefficient, which is going to be 200, which it should be the coefficient of the S squared, the S maximum square, and the B coefficient, which it should be the coefficient of the S maximum, or the variable which is S in that case, or S maximum, it is negative 98.1. You should consider the sign, and the C coefficient is going to be the negative, this constant term, which is going to be the negative of 49.05. So then you're going to plug these two parameters into the S maximum 1 and 2 just to find the roots of this quadratic formula or equation as 1 over 2. Then you're going to have the negative B. So the negative times negative gives 98.1 plus or minus the square root of the B square, which is negative 98.1 square, negative 4AC. So it is negative 4A, which is 200 times C. So the negative times negative gives here positive of 49.05. If you did the calculations, you're gonna end up with two roots, two values of the S. Depending on one time you're gonna take the positive, one time you're gonna take the negative. So the quadratic formula can be written in this way. Again, it will be as the two roots as S1 and 2 equals 1 over 2 negative b plus or minus the square root of b squared negative 4ac. So this is known as the quadratic formula. So if you plug this formula here, we're gonna end up with S maximum 1 as a first root equals, your objective is just to do the calculation for the term of this square term, so 98.1 squared plus the 4 times 200 times 49.05 under the square root. This is gonna give us the 22, or let us write the two roots again, and times half. So this is gonna give us plus or minus 110.525, and this is gonna be the 49.05, which is I just multiplied the half. Then if you take the positive one time and the negative one time, this is gonna give you the S maximum twice. So this is gonna give us two values for the S maximum. So S maximum 1, the first value, equals, and S maximum 2 equals. So you're just gonna take the positive one time as positive 49.05. This is gonna give us the 152.57, and it should be in mirror because we didn't do any changes over the units. And the S maximum 2, if you're gonna take the negative, so it's gonna be 49.0205 negative 110.525. This is gonna give us negative 61.475 meter, right? So as you can see, we end up with two values. Which one that we have to proceed with? The one with a negative, with a positive sign. Why? Because this S maximum, it should be a distance, and any specific distance, it should be positive. There is no physical meaning for a distance that is negative, but the position, it could be positive or negative. But here I'm talking about the distance. It should be scalar quantity, that it should be positive. It means that you are going to reject. We just gonna accept the positive value to indicate the, so we are going, this value will be rejected, reject this value, and only accept the S maximum. So in that case, we're gonna say that the maximum compression, this is what is required. The maximum compression in the spring, once this block A with 10 kilograms is released, is equal to the 159.57 meter, and this is what was required in this problem. Make sense? Actually, there is something that I've made wrong here, that this quadratic formula should be 1 over 2a. I forgot the a. The a, which is the coefficient of the quadratic term, this A, it should be included. You're gonna write 1 over 2 in case that a is already equals 1. So one of the things, for example, if you decided to use the quadratic formula with the form as I presented previously, I should divide all the terms by 200 first. But I was mistaken and forgot the a. It should be included here in the denominator. It means that I should divide all of these values by 200, and this also should be divided by 200 here. Right, so this is there should be an a that included. This is the correct value for the quadratic formula. So if we did the calculations anyway, we're gonna end up with 159.57 divided by 200. This is gonna give us 0. Like around 0.8 meter, and the second one definitely is gonna be negative, which will be rejected. So we're just gonna consider only the positive value. So this is a typical application, how we can use the conservative energy principle in order to solve some of the engineering application. In some of the application, you would be required, for example, to calculate the maximum compression if you decided to release. Think of it like this is a real application. How about, for example, if you have an object in the factory or in your work that you have to throw it from a certain level, and for some reason you would like to save it. You don't want to produce any damage upon falling this object down into the ground. So you're gonna set up a spring underneath the object, this spring is gonna absorb the impact. It's gonna make the impact of this object to the ground, it is less, it is lower. So for some reason, if you decided to apply a spring or even another damping system, so this spring will be compressed with a certain value. So within your design calculation for this problem or this system, you should know how much of maximum compression that should be produced within this spring. To calculate this maximum compression in the spring, you have to set up the problem in this way and apply the conservation of energy principle to end up with this maximum compression, how much it is. Make sense? All right, so that's it for today for this video. We have covered these different forms and types of the mechanical energies as kinetic energy, potential energy, and elastic energy, and we considered the application of the conservative energy principle. The next lecture or the next video, we are going to discuss the another form of the energy, which is a heat. So the heat, it is a form of the energy, and we are going to consider these for thermal application, and also are going to discuss some concepts relating to the heat transfer. All right, so that's it for today, and thank you so much for watching, and see you in another video.